the material side. So crash. Yeah, we have an understanding of crash, but unfortunately we cannot design the aircraft to all scenarios. So we have to limit it. So yes, when there is impact and substantial damage, it's a crash, but we are going to define some limits for what we're going to certify the aircraft for. I mentioned this before that when you have crash, you have horizontal speed and then vertical speed or acceleration. Each of them would affect the performance of the material. Specifically, the horizontal becomes quite important, and I'll mention it again when we go through the specific of material response. But the way we're going to design an aircraft is that we're going to assume a worst case scenario, which is a vertical speed of 30 feet per second and a horizontal speed of 17 feet per second. But it's really difficult to do tests at larger scale by having both horizontal and vertical speeds. So you can drop a fuselage from heights and they will get the vertical speed, but then horizontal, how are you going to do that? So typically you do that in simulations, not in tests, but that's where it becomes quite tricky. So keep in mind that whatever you're designing is not going to survive like a crash from, I don't know, high altitude. It's not the purpose. But if you're landing and there's crash during landing, it can survive. And that's the purpose. So with that in mind, with the limitations that we're going to impose on the requirement, let's go through this. Any questions so far? It's clear? Okay, so there are 4 things that we have to guarantee. First of all, it's a system design. It's not about the material only. There are passengers, there are seats, there are cargoes, there is the entire system that we are designing for. And each of them would significantly change the behavior of the aircraft. So keep in mind, it's a system process. In simulations, we simulate it like that. In testing, we test it like that. We have dummies and we have seats. So it's not just about composites and the fuselage, it's about everything. And then we have to guarantee 4 things. First of all, retention of mass. It's not like we're gonna lose half of the aircraft and the other half is gonna survive. No, the mass has to survive within a threshold, number 1. 2, you have to maintain a path for the passengers to exit the aircraft. So, for example, if this floor, the passenger floor collapses, it's not acceptable because then there's no path for the passengers to exit. So we have to make sure that floor beams survive. 3, the volume, survivable volume. So if the fuselage deforms significantly, it's not acceptable. Again, all of those things are for that very limited force we're going to apply. 30 feet per second vertical speed, 17 feet per second horizontal speed. So it's not a major load, but it is considerable. Lastly, this becomes quite key, what the passengers feel. So everything so far was about the aircraft. This last one is quite important. It actually leads many of the limitations in terms of load and accelerations. G-force specifically, what is it the passenger is going to feel? I'm going to talk about some of those limitations and limits that they put. Again, retention of the mass is for aircraft. The emergency path is for the aircraft. Survivable volume is for the aircraft. This last one is what the passengers feels. What load is applied on the passenger, which is nothing to do with composites, but then composites can minimize what's going to be transferred to the passenger by, as you're going to see, we're going to put in some specific mechanisms to absorb the energy. So the energy doesn't get transferred to passenger. In an impact scenario, if you design it carefully, a composite structure is much better than an aluminum structure because of the energy absorption capability. And we're going to go over that. But if you don't design it well, aluminum is actually by far better. So the design becomes quite tricky. So what are the limitations on a passenger? So I'm going to talk about G-force, and then there's a force as well. So when we feel positive G-force, that's like an aircraft accelerating, and we feel positive G-force, So the blood goes toward our legs, and our brain might feel a bit dizzy, and then there's blackout if there's significant G-force. Normal passengers, normal people like us, I think beyond 2G is a lot for us. So we cannot, maybe 2.5G, but not beyond that. So normal people, pilots, they can go to 9G if they have suits and training and all those things. But even beyond that, it's not acceptable. Negative G is quite different. Negative G is when you, let's say you descend quite fast, and then all the blood goes to your head, and this red eyes, they call it red eyes. So the blood actually comes to your eyes and you can't see. I think there's a much lower limit. I think it's 2G or 3G, even for pilots, trained pilots. So negative G is quite bad. Positive G is still acceptable. Or maybe with the suits, they can go beyond the 2, 3G. But for commercial, so this is not like fighter jets. The passengers are not gonna, they shouldn't experience those G limits. So I think, if I remember correctly, an aircraft is designed to maximum 2.5G for a very limited amount of time, maybe 5G, up to 5G. Well, that's like worst case scenario. So if it goes beyond that, aircraft breaks. And the pilot always keep the G-force below, if I remember correctly, 1.5G. Otherwise, you don't feel good as a passenger. So 1.5G is the flight envelope. The structure is designed to 2.5G. In very extreme, rare cases, 5G. So that's the G-force. By the way, this was the vertical G. The horizontal G, we are a lot better in handling horizontal G because the blood doesn't go up or down, so it stays where it is. I think the record for horizontal G is something around 47G, 48G, and this was like I don't know, like I can't remember, but I remember now you can look it up to see where it happened. But there was a recording, and so the horizontal G they can go to 47, 48G. But again, not for us passengers. I mean, for fighter jets or for special cases. So that's the G-force. So you're going to limit the G-force. But this 2.5G becomes your design driver. So you have to design the structure to survive that. Then there is the force, the maximum force that the passengers can handle, and that's for like a lumbar load or other loads. And I think I don't know if this 1,500 pounds is what you will apply for all types of load, but I think it's like a vertical load. In addition to acceleration, you will limit the vertical load on the passenger. And this is an example. I think it comes from simulation. So I know a lot of simulation is done at Boeing to simulate this behavior, but there is a facility in I'm going to say Nayar in Wichita, where they have a large facility like this for this type of test that they can accelerate horizontally and then can simulate that, but also mainly for drop tests, which you need to drop it from like a 3-story height, so it will reach the 30 feet per second. Okay, so there's also other things which duration, direction, all of these things are becoming important. Do you know what's the best case scenario? How do you survive? What should be the position to survive a crash? You have seen that it's when you do this, it's for the lumbar load, so it's gonna protect you. I don't know if I've shown you that video. There is a video that it shows like a mom. So there's a mom and a child, and the mom is holding the child with the normal force a human can hold. The crash happens, and the first thing happens, the mom cannot hold on to the baby anymore. So that's why they say, oh, protect your child first, like put the seat belt or whatever on the child as well, because you as a person cannot hold on to another child during the impact. So protect the child, protect yourself, and then go to this position, and then it increases your chance of survival. God forbid any of us are in that scenario. That's one of my nightmares, personally.
I have a question. Why do we think that you can go hold this position better than holding this position with the child?
No, the child would not, you're not going to hold on to the child. So here's the thing, they say, in most cases, if the child is below 2 years old, you're not going to buy a seat for your child, right? So the child is going to sit on your lap. But that reduces the survival rate of the child. So if there is a separate seat for the child, you can put the seat belts for the child and for yourself, and then you can go to that position. So the child is not going to get thrown away in the aircraft. So that's the problem, yeah. There's a video, if you search online, there's a video on YouTube where there's an aircraft where, I don't know if I showed it in last class, that the last quarter we had with some of you, that it's a Boeing 737 or 777, I can't remember. The pilots, they parachute out of the aircraft, and then the aircraft basically goes with all the dummies and like the sensors and cameras, and they record a reasonable, like actually an actual crash scenario. And many of these lessons learned is there. So they put in some dummies, like as moms with holding a child like that, some people like that. But then you could see even in that scenario, there's chances. So in that scenario, remember, rows 10 to 12, no matter what, they were all dead because they were thrown out of the aircraft. But then the other rows, the people who did this, they survived better. And then it was definitely not a good thing to hold on the child like that. Anyway, I have to fly in 2 weeks now. I'm a bit nervous. I scared myself a bit. Okay, so let's talk about some of the material aspects. So I don't know if you can see it properly, but there is so this is the lower section. This is the cargo beam. So the cargo goes on top of this. So it's a beam, and there are this you can kind of see here, and there's this component here, which in this case is a sinusoidal shape part. We're going to talk about that in a second, why sinusoidal shape. But there's specific components, designs, we briefly mentioned it in one of our classes. So the whole idea is that to come up with a design to maximize the energy absorption of composites. Otherwise, they're not going to be good in absorbing the energy of the crash. So you're going to have the subfloor survives the cargoes and the passengers, but you have the sacrificial parts that their job is to absorb the energy of the impact. And you know how much energy you have because you're designing it to 30 feet per second. It's not going to survive beyond that, but at least it's going to absorb some of the energy. So what is the design? If I mentioned this before again, but when the impact happens, you want this frames kind of rotate inward, and then the sinusoidal shape components, they're going to rotate inward as well and becomes vertical when they're doing the crash. So they can absorb the energy much better. So you're doing that by designing this splice plate, which is going to fail in tension. So it's an intentional weak point in the design that you know if crash happens, it's going to fail. It's not going to fail in any other cases, but the load of the crash would be enough to fail that splice, and then the beam is going to bend inward after that. So it's a weak point. And then you have this sinusoidal shaped components that are designed to basically maximize the energy absorption. And the shape has a significant impact. We're going to talk about that. Is this clear so far? I think it kind of shows scenario here. And again, you do this with cargo, maybe without cargo. So you have to have the different scenarios in mind. But here is the passenger floor, and this is the cargo floor with the beams. And you can kind of see how the lower parts bends inward. And then this one has multiple components, crash absorption components. And this is the design of 787. So 787 is designed like that. So you can basically calculate how much energy each of these components can absorb, and then it becomes, it meets the criteria of crashworthiness. Okay, so let's talk about energy absorption from a material perspective. If you have an aluminum tube. Let's say rectangular tube. For aluminum, it doesn't matter that much, but let's say rectangular because it becomes important for composites. And you start crushing it. So the way you're doing tests is that you will secure it vertically, and then you drop a huge weight from like I don't know, from 10 meters or from 15 meters or 5 meters or what, and that sets the energy of the impact. And then if you're designing it properly, if this doesn't buckle, because it might buckle. If it buckles, then that's a different story. It's not going to absorb energy. If it doesn't buckle, it's going to create local plastic hinges. And then it will go through this, and it will create multiple plastic hinges. Plastic hinge means that it's absorbing energy. Because basically, if you look at the stress strain curve, it basically goes through that yielding process, and the area below a stress strain curve becomes the amount of energy per volume that you're absorbing. So that's where you can take advantage of the material behavior. If it goes through yielding, better. Multiple of these you have, even better. So a case like this is the best case scenario that you might have for a metallic tube. If you don't design it properly, it's gonna buckle. Then it's only have one plastic hinge, and it's not maximizing the performance of that tube. So that's the idea behind metallic structures. But for composite, it's very different, right? So here's a comparison of an aluminum failure versus a composite failure. And here I have rectangular tube versus circular tube. And you can see that the failure is different. So in best case scenario, imagine that you're taking every fiber, and during crushing, you're breaking it over and over and over again. So you have a fiber that breaks, it doesn't buckle, so it breaks under compression over and over again. That absorbs tons of energy. But sometimes the design is such that it doesn't do that. And you can kind of see it here. It basically, if you think about it, that compression happens here, then at the corners, you will have tensions. So it's like a Poisson's type effect. So it's gonna cut the corners in tension. And then it will create this type of bending in the corners that have been broken. And that's what you see basically there. I forgot the name of this failure mechanism. There's a name for this type of failure mechanism. Does anyone know? I forgot. Anyway, so it's a different amount of failure, as you can see, energy, that's as you can see, because now you're bending the fibers and breaking them. Here, you were crushing the fibers one by one. So this should absorb more energy. But overall, if you design it well, this will absorb more energy than aluminum, because aluminum would be like, I don't know, 5 hinges, 6 hinges. Here you're breaking the entire column if you design it properly. But then this breaking the corners and bending the sheets actually is to your disadvantage. This reduces how much energy it can absorb. If you can make it such that it doesn't break and bends, then it will absorb a lot more energy. So sharp corners in general are bad. It will be a weak point that you can break that corner in tension. So you don't want to have that. So the main thing that we measure, it's a very messy process, as you can see. I mean, how do you measure this? When I was a PhD student, we had to simulate this, and it's a nightmare to simulate something like this, right? So there is one parameter that you look for in the performance of any component, and that is called specific energy absorption. You do a test, you plot force versus displacement, and then the area below the curve becomes how much energy was absorbed, and then you divide it by the mass that was crushed. And so it's energy absorbed per unit mass of crushed material, kilojoules per kilogram, for example. So first of all, if you're comparing aluminum and steel with composites, you're dividing it by mass, so the density of composite is lower, so it's to their advantage. But kilograms to kilograms, which one is better? Because for flying, it's better to have lighter components that absorb energy more. So if you have a metallic components like steel, and we're talking about circular, it can absorb 10 to 17 kilojoules per kilograms. And again, steel is quite heavy. If you replace it with aluminum, you will increase it to 15 to 25 kilojoules per kilogram. If you have short fiber composites, so not long fibers, so chopped short fibers, it's pretty low. It's probably comparable to aluminum. But this is where it gets quite interesting. If you have composites that they have long fibers parallel to the crushing load, then they can absorb a lot more energy compared to metals, right? But they have to be designed properly, and not just the design of this component, the design of a structure. If you remember from, I think I mentioned in previous classes, but imagine there are these components, and again, this is the floor beam, and during the crash, they don't get aligned with the load for whatever reason. One reason is quite obvious. Let's say this joint that you designed here doesn't fails, and then this doesn't bend inward, and they don't get aligned with the crash direction. So that means that the load would be at an angle to them. If the load is at an angle to a composite tube, it's going to break in one point in a very brittle manner, and it's not going to absorb any energy. I mean, it's going to absorb some energy, not a lot. So it's not going to go through this process of crushing to absorb a lot of energy. It becomes a brittle component. So a couple of years ago, I would say 10 years ago, everyone has started doing research on creating crushing component for automotive industry. So let me excuse my drawing, but let's say this is a car, and let's look at the design here. So the idea was to have these tubes installed here, 2 of them, let's say, and in a crash scenario, those tubes would absorb a lot of energy. So to protect, so it's a front impact, it's going to protect the passengers. The problem is that how do you know that the load comes exactly parallel to those tubes? It might come from this direction, and all of a sudden they don't absorb a lot of energy. So I remember at that time we were doing projects with Honda, Toyota, all of them, Ford. Everyone was spending millions of dollars to design proper tubes because they wanted to reduce the weight of the car. At that time, that was before electrification and Tesla, all of those things. And then after 10 years, they realized that it might not work because you never know which direction the load comes in. So in the new, they replaced it back with aluminum, from what I can see. So we are not using composites to absorb the energy of impact at the moment in automotive industry. But for aerospace, yes, we do this. But we have to make the design such that the components align themselves with the crash. But then people started doing a lot of tests, and many of these tests were done in, I don't know why. Where's Professor Dan Adams? Utah, University of Utah. So he did a lot of tests in that university with different shapes of these tubes. And it's not just the shape. Actually, when you do the test, it becomes how you do the tests. What are the boundary conditions? And people also realize that if they have flat top surfaces, or it has to be like a tapered edges like that, it would have a huge impact. I don't know if you can kind of see it, but it's like kind of like tapered at the edge. It might become a difficult measurements if you don't have this tapered ends. Anyway, so there's lots of details in the test, but they realized that if they change the design, the energy of the energy absorption capability changes significantly. If you have a tube, that's where the energy is around 40 kilojoules per kilograms. Still much higher than aluminum or steel. If you have a corner, now there's still one corner that fails in tension, let's say, and you start bending the other component, but it's still better than tube. So it increases the energy to around 50 to 60. And the best case scenario is something like this, which doesn't have a sharp corner, because there is no corner to break, and then the rest will go to bending. So you will start crushing everything. So you can increase the energy to around 80 kilojoules per kilogram. So the design has a significant impact on how much energy you can absorb. Is this clear? Any questions so far? Yes.
What is the weave pattern on that example?
Okay, so I think it is a woven composite, it's not UD. I can't remember why, but I think it will help for delamination, perhaps. So I think the other thing would be the impact happens and then the layer just falls apart, so they don't keep, so the delamination becomes a dominant failure mode, or splits becomes a dominant failure mode. So I think that prevents that, but I might be mistaken. I have to look it up. So they did a lot of these tests in Utah, the University of Utah, and they put it on a nice website. You can actually go and see all of these videos, and you can see the curves. It was paid by FAA to produce it and then use it for design of the next generation of aircraft. But now I can't remember what material they used and if it was woven, all of them or not.
Would you suspect that if it was unidirectional, it would have a lower SEA?
I think so. I think so, yeah. But this is me guessing now, thinking that if it might promote or not promote delamination. Okay, so a certification program might be something like this. And again, there's tests and simulation in every step. You start by doing some coupon tests and simulations, like bonded joints under compression. Then you would go to one level higher up. This is the tube crushing we were discussing. This becomes quite key in designing and certifying your design at the end of the day. So you will do tons of these tests, hundreds of these tests, and these are quite expensive tests as well. Subcomponent is where you might do tens of tests. So you will start adding the frame and some of these components. A component is basically you have a section of the fuselage, and then you have some of these components and the beams. You can kind of see how the simulations or test is done. And then all the way to a full scale. I don't know how many full scale tests you do, but you do a test and simulation again. And then you compare, and then that certifies the crash scenario. And for all of these things, again, you assume 30 foot per second vertical and then 17 horizontal. But in the test, as I mentioned, you can kind of see why it's difficult to actually create that horizontal direction force as well. So you just drop the component from vertical, and I believe you just rely on simulation to certify for the horizontal component. I had a friend in German Aerospace Center, and his job was to do all of this designs and testing and simulations. And sometimes when we were discussing, he would say that I would never fly. He would prefer in Europe to just go by train or by car. I asked him why, and he said, because I know how these things are designed. They're not going to survive. But anyway, again, going back to the point of this is not to survive any crash scenario. It's not going to survive that. It's a very limited design, maybe for crash landing, so something very close to the ground level. But again, you have to be careful even in those designs. Any questions before I move on to the next topic, which is fire? And I have one more thing, and that goes into the challenges of simulations. Simulating something like this is extremely challenging. When we were doing simulations of these components, it was, I would say, 4 to 5 hours for each simulations. And the reason is that when you have short events, traditional simulation methods, they don't work. So you will rely on something which is called, just for your own information, called explicit simulation. Explicit simulation goes to extremely tiny time scales, 10 to the minus 6 seconds, 10 to the minus 7 seconds, and does Newtonian calculation in that scale. and then just add to the next scale, to the next time step. So it becomes an extremely long process to simulate it. And shorter the time scale, it becomes more accurate. So it works, let's say for 2, 4, 5 hours. If you want to simulate this thing using that method, it's just going to be months before you can get any simulation results. So it might be cheaper just to do tests at that point. So people have developed different approaches. You can kind of see one of them here, which they come up with this, they call macro elements. So you put like these beams together, which is not exactly like the real structure. It's sort of like a representation of the real structure. And that helps you to kind of understand the behavior of an actual aircraft. But there is problem. What are the problems? The testing at larger scale is very difficult. Then simulation is very difficult. So at larger scale, we have challenges for both test and simulation. So keeping that in mind, that adds more to the complexities of the problem, certification problem. Okay, let's move on to fire safety. So first of all, there is this, let's say, viewpoint that composites are not safe compared to metals in a fire scenario. And what are the fire scenario? In-flight fire, post-crash fire, or the gas tank fire. So there are 3 scenarios, and you're going to design the aircraft for all 3 scenarios. That's a true assumption if you're not careful with the design. But since that perception exists, FAA has gone the other way. It says that in all of these things, you have to show that your design is better than an aluminum design. So that's this extra safety factor. So God forbid, in the case of fire, it's safer to be inside a composite aircraft than a metallic aircraft, just because of that extra safety factor that FAA mandates for designers to show. So how do we show them? And let's go through some of the details of that. So for each of these 3 fires, for in-flight fire, you have to prevent propagation of fire. Post-crash fire, you have to have enough time for passengers to leave the aircraft. I think it's around 1 minute. So you have to show that the aircraft's structure survives if there's fire, and that 1 minute lets the passengers to leave the aircraft. So you will show that 1 minute, I think, through simulation typically. And then reduced vapor flammability, that's the other thing you have to show for the wing. So I mentioned this before, the aluminum seems to be safer. For example, in metallic structure, it doesn't burn at the same temperature as composites. Composite is going to burn at lower temperatures. And metallics are better in dissipating heat because they have much higher thermal conductivity. So as a result, oh, sorry, there was one more thing. Yeah, I think I mentioned this. Where's the FAA thing that they want to mention? Did I put the FAA? I think I didn't put the FAA statement somewhere. Oh, yes, here, okay, sorry. That's the FAA statement. It says, we must demonstrate that these materials are at least as safe as aluminum when you're designing. So that's the mindset. So how do we do that? We're going to come up with some tests. We're going to measure what toxic materials are released, how fast the fire is going to propagate into the material, and how long they can survive. So we will check all of those things. Out of all of these things, we have changed the formulation of the material, not just for the fuselage, interior materials. So you have to look at everything, what you cover the seats with, the interior decorations, but also the structural components. And then coming up with tests. So for example, this is one of the tests, a larger scale test. You will get a section of the fuselage. I think this is from, this is Boeing 707 fuselage. And then you will put this metallic sheets around it to create exposures area to heat. and there's this pan that will create a large fire in that pan. And then I think in this case, it's 55 gallons of jet fuel. And this is basically resembling the fact that the wing caught fire. And then you will look at how long it takes for this thing to survive, and also what comes out of it in the interior, how much the temperature rises, and then do you have 1 minute at the end of the day to survive or not? So the passengers can leave. So that would be like the test version. And then you can do simulation. Simulation is a bit tricky, but I've seen some good simulations for this process. But test becomes quite important. And you do test at the material level. I've never done these tests myself. We didn't have the facility to do this test. So these are very specialized tests. And then this level, I've never actually seen in person, people doing this test. Okay, any questions so far about the tests for fire safety? So it limits the formulation that you can use for composites. There's a lot of innovations in the resin formulation to survive fire or have fire retardant material additives added to the composite formulation. So there was an accident in 1996 where we can kind of see that the wing is gone now. There was an explosion on the wing, and it was not a composite. Was it a composite wing? I can't remember. No, it was not a composite wing. But there was lots of lessons learned, and FAA came up with a solution for composite wing eventually. And that is, on every aircraft, there should be an inert gas generator system. So if you don't have that, when you start using the fuel and then you have a half full gas tank, you will end up with fuel vapor. Fuel vapor, composite, sparks, you will have fire. To prevent that, you're gonna pump in nitrogen into the gas tank continuously. And that inert gas prevents the fuel vapor buildup. So on every 787 aircraft or other composite aircraft, there is one of these nitrogen generators. I'm gonna move on to lightning strike, which for me is the most interesting topic. I'm gonna explain to you why, but any questions? Fire safety. Yes.
You said that, so for composite airframes, you're required to prove it is safer than the aluminum design.
Yeah.
Is that like a component level requirement that you just have higher standards, or do they have to sort of like construct an equivalent aluminum design from model one and show that it would be safer?
Right. So I think there's some requirements on the, let's say the 1 minute, which it might be incorrect, the 1 minute that I mentioned. So you have to go and check exactly. But let's say the time wise, they will show a higher safety within composite fuselage than a metallic fuselage. I don't know if they're not going to build the exact same thing out of aluminum. Maybe in simulation you can show that, but also for material itself, the kind of test that you can do at the lower level, you can kind of test them on metals and composite as well. But this talks about materials, not talks about the design. So, but the design itself, I know you have to show that the fuselage would survive longer than aluminum fuselage. I think that makes the design quite thick and heavy as well. So it's an additional safety factor on top of all the other safety factors we have had so far.
Are they like aluminum frames, or is that a new thing that they have to develop?
No, they don't need to develop new things either. Yeah, that will be too much expense to. Yeah. Okay, so lightning strike. Every year, every aircraft would experience one lightning strike on average. That's the statistical measurement. And then if you have a metallic structure, the energy comes in. Metals are quite good conductive. They disperse the energy. So nothing happens to the structure. But then composites, on the other hand, carbon fiber, it's a good electrical conductors compared to resin. But aluminums are 1,000 times better than carbon fibers. So energy of the lightning strike comes in, it doesn't have enough time or enough pathway to get dissipated. It gets absorbed in that location. And it's going to burn through the composites. If it's carbon fiber, if it's glass fiber, which is not conductive at all, it's going to puncture through the material. Worst case scenario, that puncture is so fast that you might end up with pressure built up below the surface, and that will lead to explosion. So carbon fiber, glass fiber, metals. Metals are 1,000 times more conductive than carbon fiber. But then carbon fiber is still by far better than glass fiber. And resin is not conductive at all. So lightning strike happens. How do we guarantee the survivor of composites? Keeping in mind that this event happens in 2 microseconds. First of all, from a simulation perspective, we are very limited. I've talked to people who are like experts in this at Boeing. They have done this for 30 years. We still heavily rely on tests. So there are tests setups that can simulate the lightning strike. We used to have one here at UW in AA departments, and the PI left and he took the machine with himself. But it's a very cool test, I would say, that you would actually test it. And there's some requirements, what you have to show. What you have to prevent is spark. If there is any sparks, especially near the gas tank, you will get fire. So in any of these tests, you will make a design, you will do a lightning strike test, and there are special cameras that can record if there was any sparks or not in like microsecond. And if there is any sparks, that's an invalidated design. So I'm going to talk about where sparks might appear and how we do this test. But here is a typical scenario. It's a composite which was unprotected, let's say. So lightning strike comes in, energy build up locally, and it's gonna, in this case, it's carbon fiber, so it's gonna dissipate the energy a bit, but it's gonna damage the part. If it was glass fiber, it was a very different story. It will just puncture through it. And again, keep in mind, this is gonna happen every year. So you cannot have this on an aircraft as a damage. Here, I think is the same scenario, aluminum versus composites, and this is unprotected carbon fiber composite. I'm going to talk about protection. And this becomes quite small compared to damage that you see here. And you probably don't see, so there's resin burn off, resin goes through pyrolysis. There is probably delamination. You're going to probably break the fibers. But the extent of damage is probably a lot more extensive than you can see in this corner. But this corner is probably completely gone because of the temperature that is experienced. Here's another example that it's a puncture through the composite. And this happens if the design is a bit thin. If you have a thin design that cannot handle that amount of energy, then it's going to puncture through thin design. So at very critical locations, you have to either increase the thickness of the design, or better thing is to add a metal layer on the outer surface. And that metal layer job is only to dissipate the energy from critical locations. So we'll come up with different strategies to do this. And having said that, this area of how you create some protection against lightning strike is one of the heavily guarded in terms of IP. It's not in public domain at all, many of the details of how they're doing it. There's some insight, which I'm going to go through it. There's some information in public domain, but it's a closely guarded secret of how this is achieved. And most of it is from the material design perspective. How do you design specific layers that can handle the lightning strike? We have some information which I will share with you. But again, this is one of those exciting areas, which unfortunately is all done typically within companies. So if any of you get hired by, let's say, Boeing, the next day you can go and look up that secret documents, and you will have a lot more information than I have to share with you now. So keep that in mind. So I'm going to share with you what I've learned from public literature. And I don't know the secret sauce, what's this actually happening behind the curtain, okay? Yeah, talk about this. Okay, so there's a couple of scenarios. I'm going to go through it. What are your knobs? First of all, you have to minimize lighting damage at critical locations. So we're going to learn how we can do that. You definitely have to prevent puncture through the composites. So you have to dissipate energy in the area that there is possibility of puncture. So you might add metals on the outer surface in some cases. But this second one is the most interesting one, which I'm going to talk about, because I have seen that in almost every composite aircraft. That is adding a copper or bronze mesh or foil on the outer surface. I'm going to talk about it in a second. Conducting paints doesn't work. That far I know. So there's people that do research and they come up with by adding metal components into, I don't know, resin paints, and it doesn't work in dissipating the energy. It's not as effective as a continuous metal. And this is quite critical, but also very subtle. So electrically bond structural parts, and it's very difficult to actually prove that. I'm going to show you why and where it becomes quite important. Think about this detail. Let's say this is your gas tank. So this is the U-shaped spar. There's a top skin and bottom skin, and this becomes your wing eventually. So you have to connect this U-shaped spars to the skins, so they're fasteners. And this would be the outer surface where the lighting strike occurs. So here is your gas, and here is the lightning strike. How do you protect this extremely sensitive structure? First of all, you would put a layer of metallic mesh on the outer surface. And I'm going to show you a design of that. And that's dissipate the energy. And there is this law, I forgot, that when the lightning strike happens, the electrons are mostly gathered on the surface. As you go through the thickness, they exponentially become less and less and less. They don't dissipate. But if you absorb the energy, most of the energy on the surface, it's quite good. It's not like we are leaving a lot of energy to go inside the material. So let's say we are absorbing, I don't know, 90%, whatever of the energy. The fastener itself is conductive. You have to use metallic fasteners. So it becomes a way for the energy to go toward the gas tank. So you will prevent that by putting a layer of, let's say, glass fiber, which is not conductive, under the fastener. And then you will cover the surface with non-conductive paints, let's say epoxy, which is non-conductive. Every corner that you can find, you will do that. You will put this putty material, which is like epoxy with some additives, and it protects that surfaces. So what are you protecting? Sparks. You don't want to have any metallic area with gaps around it. If there's metal conductivity and gap, there's a spark. And then there's fuel vapor that's, some of it still remains, even with gas, with inert nitrogen inside. So that will create fire. But that gap becomes quite tricky. And it goes back to the design here. You will drill into composites, and then you will put the fasteners inside. If there is any gap there, you will get sparks. So the drilling design is quite key. So if there's a limit, I forgot, that you have to make sure the gaps are not within the certain threshold or you will get sparks. So that's kind of guarantees that your design of the fasteners is good, but then the quality of drilling becomes quite important as well. So what I have seen is that they make coupons representing the bonding points, let's say multiple fasteners, and then take it to the lab and they test it with the fake lightning strike. And if there's any sparks in any of the fasteners, that means that you didn't certify that design. So they will go back and redesign it. And the number of fasteners, their spacing, all of that becomes key. Basically, you have to guarantee energy comes in, get dispersed around the fasteners, doesn't go toward the gas tank, doesn't create any sparks. So it's a very detailed design. And again, most of it is secret, trade secret of how they're doing it. And what I'm sharing with you is in public domain. Any questions? So this is the type of test that I could find online, at least. So it's a composite plate, and you will integrate your design on top of that. So the paints, the foil to dissipate the energy, anything that you want to design, the fasteners is integrated into this. And then this rod basically creates a lighting strike on the surface. You will measure the amount of energy that goes into it. You will measure the amount of damage. You will measure if there is any sparks, and then that will be the outcome of the test. There's a special cameras that they can record sparks, and there is like a threshold. If they record any red light beyond a certain, I don't know, colors, then that means that this was a spark. So it kind of like disproves it. So it's not someone standing there say, oh, it's sparks or not spark. It's all digitally done. This is one design that you can see online. It's not what I think eventually implemented is 787, but something similar to this. So there is a composite fuselage, let's say. On top of that, you will put a copper mesh or copper foil. So I've seen foil in 777X. For 787, I don't know if they use like a mesh like this, or I'll show you. So the foil would be like a lot more condensed than this, but I don't have a picture of the foil to show you. But this is, for example, produced by a company called Hexcel, and they have a good name for this, lighting strike protection interwoven wire fabric. It's the name of that design. That it's a layer that comes in and you place it on top of your composite layer. It might be embedded in another like a resin layer. So it's like a flexible resin layer with embedded mesh that goes on top. Then you would put your primer and your paints. Sometimes I have seen they put one layer of glass fiber, maybe under this. I can't remember. It could be also for the surface finish. So now I can't remember now I mentioned that. So is it on top of the? Anyway, there could be a layer of glass fiber added to this list. And this paint and primer are also UV protectors. And so the UV protection comes from paint and primer, and this copper mesh protects against lightning strike. And here is finally the entire design of 787 for lightning strike. This metal mesh are embedded on the top surfaces of the aircraft everywhere, on the wings and on the fuselage. You can see. Hopefully that's more clear, that metal mesh. Then this is a design that I mentioned. These are, so this is copper/bronze mesh. Oh, what happened? That's the edge sealant that I mentioned to make sure there is no gaps for sparks. These are coated fasteners. In addition to that, you have this nitrogen generator that pumps in inert gas. So there are three strategies if you think about it. There's tight fits, make sure there's no sparks formation. Any gaps that you see, you will do sealants. You will embed this metal mesh, and you have the nitrogen generator. So all of these are there to guarantee that you can distribute the energy of the lightning strike and protect the gas tank. Any questions? Yes.
So it seems to me that they're really trying to anticipate for a lightning strike happening to the gas tank, since that could lead to an explosion. I'm wondering if they also try to like mitigate the likelihood of a lightning strike striking the wings or the gas tanks by like having essentially a lightning rod or something elsewhere on the.
So somehow you have to like guide the energy toward that point, right? It might not happen. So I don't know if I've seen it or not. Maybe it is, but it's probably not the main design aspect. So these are what you will do. protect the wing with all these details, put the metal mesh on all other surfaces that they might experience lightning strike. I don't know if they put it under the aircraft or not, or just on top surface. That I'm not aware of that. Then in very critical locations, let's say that the joints that I showed you, you will put metal mesh. So proper metal, sorry, not metal mesh, metal plates. So you put like a thick metal plates, and that guarantees that the energy just gets dispersed quite fast. So you don't even rely on the metal foil. You will put like a proper metal joints cover for the top surface. Then you also have to pay attention, glass fibers versus carbon fibers. Wherever you have glass fibers, it becomes a lot more important to protect it even further. So you might have like a cover of metallic sheets that goes on top of the glass fiber section. These are, again, as far as I know. Yeah, there are many things that I don't know, especially about the formulation of the material, what is the current technology they use. And whenever I talk to Boeing people, I feel like the guard that they don't talk about any of those things. They have been warned not to talk outside of Boeing, probably. So it's understandable, but I think that's the exciting part. I really want, hopefully one day I would get to know more. But anyway, so yeah, hopefully that answers your question. That it's probably, from what I understood, it's always a multiple strategies. You cannot rely on one thing for composites. Other questions? Next week, March 15th, is our exam. That's Wednesday, and it's going to be from 4:30 to 6:20, 110 minutes, 5 or 6 questions. Let's say 6 questions with more focus from the discussions after the midterm, but 20%, 25% from before midterm. It's going to be online on Canvas. You don't need to come to class. Actually, I'm not going to be in the class. You don't need to connect to Zoom. And yeah, that's for the exam. Hopefully this has been a helpful course. My aim was to give you lots of, first of all, learn terminologies, but also go a bit deep into some of the terminologies, but it's a very vast topic. So if you end up working in this industry, hopefully you can learn a lot quicker than if you didn't have this course. So that was my main aim. Hopefully you've enjoyed the course. I'll see some of you around next quarter, hopefully. Thank you very much. Have a good rest of the day and rest of the week. Prepare for the exam. Thank you. Thank you. Don't forget to review the course.